triangle trigonometry. Just to review what we've done so far, we have basically seen how to use the law of sines to solve triangles that correspond to either AAS information, that means two angles and a side, which is the same thing as angle side angle, which is the same thing as angle angle side. It really doesn't matter which side you're given. If you're given two angles and one side, these three cases are the same. It doesn't matter if the side you're given is like in between the two angles or not. Oops, I meant to write SAA here. Anytime you're given two angles and a side, you use the law of sines, and you get the remaining sides and angles of the triangle. You did that in the first homework that you took after the quiz. In class last time, we talked about the SSA case. That's the case where you're given two sides of a triangle and a non-included angle. What I mean by non-included is that the angle that you're given is not the angle in between the two sides that you're given. This is what I called the ass backwards case. This is the case that sort of weirdly can have three different situations. SSA information could correspond to just one triangle, or it could actually correspond to two different triangles, or even no triangles. Today, we're going to talk about the remaining cases. So these are two of the cases that you can be given, two of the sets of data that you could be given about a triangle. Today we're going to talk about SAS and SSS. In other words, we're going to talk about how do you find the remaining sides and angles of a triangle if you know two sides and the included angle, right, where the angle is in between the two sides. So that's different from this, where the angle is not in between the two sides. And what do you do if you're given just three sides? So the key tool for these two cases that we worked on last time was, of course, the law of sines, right? That was the primary tool that we used to solve these kinds of triangles. To solve these two kinds of triangles, SAS or SSS, we actually have to use a different law, and that's the law of cosines, okay? So I think maybe next time I'll do the derivation and show you where the law of cosines comes from, but today I just want to give it to you and show you how to use it. So what does the law of cosines say? So it's a formula, like it's an equation that relates the sides of a triangle along with the angles of a triangle, and here's what it says. It says that, so if we have a triangle, say capital A, capital B, capital C are the angles, and little a, little b, little c are the sides, the law of cosines says that little c squared, that's the side length, is equal to little a squared plus little b squared minus 2 times a times b times the cosine of angle capital C. All right. So that's the law of cosines. Not quite as nice and clean and friendly as the law of sines, but there it is. It turns out, though, the law of cosines is actually really useful. Like, it's really important. I want to sort of emphasize the structural features of this equation. Namely, what I want to point out is that the side that appears here, so that's little c, is the side which is opposite of the angle which appears here. So that's capital C. And everything else in the equation, this A, this B, this A, this B, are just the other two sides which are not mentioned here, okay? And the one, I sort of tried to convey this with the law of sines as well, but I want to convey it here. Again, this equation, seems to depend upon the labeling that you impose on the triangle, but like it really doesn't. I mean, you should really think of it structurally, okay? Like, given this labeling scheme on the triangle, there are actually three different laws of cosines that we could write down. Here's the next one. I could instead choose to write, say, b squared here. okay? And write a formula for b squared. You know, it's going to be very similar to this one, except, you know, some of the letters are going to be different. You know, what are the letters that should appear? What I want to emphasize here is that whatever side appears here is the side opposite of the angle that appears here. Okay, so whatever's floating around in this part of the formula, I know that it's going to end with cosine of what? Well, what's the angle opposite of side B? Well, it's angle B, okay? And then, you know, what are the sides that will be floating around? It'll be some side squared plus some other side squared minus 2 times the product. What will the sides be? Well, just notice in the original equation, A and B are the sides other than this one, right? Similarly, the sides which appear here are going to be the sides other than this one. In other words, they're going to be little a and little c. So I can write a squared plus c squared minus 2ac times cosine of b, right? And that's another way of writing the law of cosines. And you could even do it, you know, starting with a squared, right? You could write a squared, and what would it be? Well, you know, I mean, once again, the angle which appears in the cosine function is the angle opposite of the side which appears here. That would be capital A. And the sides floating around in this part of the equation are just the sides other than this one. So that would be B and C. So I could write B squared plus C squared minus 2BC times cosine A. It's really good to think of it structurally in this way. Don't get too hung up on the labels, because the labels in the formula depend upon how you label the triangle. It's better to just sort of recognize the structure. Whatever side you put here, you can put whatever side you want right there. Doesn't matter, okay? But whatever side you put here, you'd better put its opposite angle there, and you'd better put the other two sides floating around in here. As long as you follow that rule, you don't have to worry about the labels, okay? That's really important. Okay, so let's see how this thing actually gets used. Let's start with an SAS triangle, okay? So suppose that little b is 20, and C is 30, and capital A is 60 degrees, okay? And what I want to do is just find the remaining missing angles and sides. What you should always do is draw a picture, right? You should draw this thing. So, you know, I don't know exactly what it looks like, but I'll call this A, B, and C. So I know that this is 60 degrees. I know that little b is 20, and I know that little c is 30, and this is little a, which we don't know. So we have to find little a, we have to find angles B and angles C. So what you want to do basically is write down the law of cosines in such a way that there's only one unknown in the equation, okay? Like, there are a bunch of ways that you could use the law of cosines here, right? I mean, we have 3 different sort of versions of it here, right? You could apply any one of these 3 to this triangle, right? But we'll make it so that you only have one unknown in the resulting equation, which is what you want, right? It turns out that if you set it up using A as the side that shows up on the left-hand side of the law of cosines, like if you use this version, then you'll only have one unknown, right? Because A is unknown, right? Okay, so that'll be my unknown. But notice that little b and little c, I know both of those, okay? And then the only other thing in this equation is capital A, and I know that. So if I use this version, then I'm only going to have one unknown. If you write down the law of cosines and you find that you have 2 unknowns, then you just need to use a different, you know, version of it, okay? So, so this is going to give me a squared is equal to, so b squared, that's 20 squared, plus c squared, that's 30 squared, minus 2 times b, which is 20, times c, which is 30, times the cosine of a, which is 60 degrees. And I just need to simplify this expression, and that'll give me a. So a squared is, let's see, what is all this? So for one thing, when evaluating this right-hand side of the expression, you know, remember your order of operations. You cannot combine, like, the 20 squared and the 30 squared with this term here until you have to evaluate this whole thing first. You know, multiplication first, right? So take care of the multiplication stuff before you try to combine these terms. So so 20 squared is 400. So 400 plus 30 squared is 900. Minus 2 times 20 is 40. Times 30 is going to be 1200. So this is minus 1200. And then cosine of 60, I could use my calculator to get cosine of 60, but 60 is actually a unit circle angle, right? I know what it is exactly. It's 1/2, right? Okay, so this is like a squared is equal to, let's see, this term here is really 600, right? So it's 400 plus 900 minus 600. So 400 plus 900 minus 600 gives me 700. And then, I take the square root of that to find a. And I get like 26.45, right? You could write an exact answer if you wanted involving radicals. I'm not that worried about it. 26.457 is good enough for me, okay? So that's little a. Well, so that gives you little a. Now, how do you find the remaining unknown information? We're now missing these two angles. How do you find them? What you have to do is use the law of cosines again. All right. Now, I want to point out, it's possible, or it seems like it's possible, to use the law of sines on this, right? You could say sine of 60 over a is equal to sine of b over 20, right? And then solve for b. But you really shouldn't do this, okay? Do not use the law of sines on this triangle. If you remember at the beginning of the lesson, I sort of categorized all the possible triangle information into two categories. This first category, which we talked about last time, and this second category, which I'm talking about today. On this category, when you have angle, angle, side, or side, side, angle, you should use the law of sines and the law of sines only. When you're given SAS or SSS data, you should only use the law of cosines, okay? Do not mix and match these things, all right, within the same triangle. The explanation for that is a little subtle, but basically, if you think about it, if you tried to use the law of sines on this, you'd wind up with an unknown angle B, and there'd possibly be two base solutions, and you'd have to think about which one is right. And it turns out it's a very delicate issue, and just don't do it, okay? So instead of using the law of sines to find angle B, just use the law of cosines again. Now, how do you do that? Well, we want to set up a law of cosines relationship where we only have one unknown, and we can do that if we write down this version of the equation, right? If I want to find angle B, then I should use the equation involving angle B. That's this one right here, right? And I know everything else in the equation. So let's go ahead and use that. So I have, let's see, so I have little b squared. What is little b squared? That would be, this is b, right? 20. So that's 20 squared is equal to a squared. That would be the 26.457 that I just found, plus c squared, which would be 30 squared, minus 2 times a times c, so that's 2 times the 26.457 times c, that's times 30, times the cosine of angle b, right? So I've just used this second version of the law of cosines right here, and as you can see, capital B is the only unknown, so I can solve for it. People tend to make a lot of mistakes when they solve this equation for B. You need to simplify things, but all right, so for one thing, you can't combine this thing with this thing right now, okay? You can't combine those two terms. Basically, this is a term involving a variable, and that's a constant term, right? It's a bit like, people tend to think that, oh, you can combine this term with this term. You can't, because it's a bit like saying this is 8, and then this is 7x, right? This is a term involving a variable. This is a constant term. You can't combine those, right? And same thing here, right? This is a term involving a variable. That's a constant term. They're not like terms. You can't put them together, so don't. Instead, what you should do is, first of all, we should square all these things, right? 20 squared is 400. 26.457 squared, that's actually 700. And then 30 squared, that's 900. Minus, and then what is this? 2 times 26, whatever this is. So 2 times the 26.457 times 30. That gives me 1587.42. So 1587.42 cosine of b. Okay. Again, the mistake that people make is they try to combine this number with these two numbers. They take 700 plus 900, and then they subtract this number here. You can't do that. Okay. It's a bit like if you had 700 plus 900 minus 1587.42x. You certainly can't combine these two terms, right? They're not like terms, and they can't be combined. Instead, what you have to do is begin by isolating the term containing the variable. That means get this term by itself. So get that term by itself by subtracting the 700 and by subtracting the 900 from both sides. Okay, so 400, take away the 700, take away the 900, it's negative 1200. So I have negative 1200 is equal to the negative 1587.42 cosine b. Notice, by the way, the minus sign is attached to this term. When you eliminate these two terms, that minus sign stays, right? Okay, and then to get the cosine b by itself, you divide both sides by the negative 1587, right? So I'll take that negative 1200 and divide by negative 1587.42. Okay, so I got 0.7559. Okay, is equal to cosine b. Well, that is a trig equation, right? And we know how to solve it, right? That's not a unit circle value, so you have to use your calculator. Let's make sure that I'm in degrees. I am, okay. So I'm going to take the inverse cosine of 0.7559. Okay, I get 40.89 degrees. So 40.89 degrees approximately is b. Now you might be saying, well, wait a minute. Isn't there another base solution to this equation? There would be. In radians, if you remember, the other base solution for cosine is 2 pi minus the first. In degrees, that would be 360 minus this first one. But think about what that would be. 360 minus that angle we just got is 319 degrees. That angle cannot possibly be an angle inside of a triangle because it's bigger than 180. And as a matter of fact, that's what always happens. When it comes to the cosine function, when you use the law of cosines, you never wind up with two possible solutions for the angle. That is only something that happens with the law of sines, okay? With the law of cosines, you don't have to worry about multiple solutions or no solutions or anything like that. The law of cosines is kind of a lot more reliable. The angle that it will give you is always just the right answer, okay? Anyway, so that's angle B. And then now that you know angle B, you can figure out angle C really easily, right? Because if we know angle B, we know angle A, then you just subtract from 180. Okay, so that's SAS. As far as the SSS case, we've kind of already seen how to do it, actually. So let me just quickly, I won't even do the whole thing, but let's just suppose you have SSS data. That means you're given 3 sides. So A is 6, B is 9, C is 4. Okay. Start by drawing a picture. I'll call this 6, 9, 4. It doesn't matter. I don't care if it's to scale or not. It doesn't make any difference. So the only thing you can possibly do here, obviously, is find an angle, right? And you're going to use the law of cosines to do that. Let's be careful with our labels. This is the side opposite of angle of A, so this must be capital A. This is the side opposite of little b, so this must be capital B, and this must be capital C. So, how do you find one of these angles? We actually already did this. It's the same thing that we just did, right? In the last problem we did, we had to use the law of cosines to find this missing angle, didn't we? We had to find angle B right here. It's exactly the same thing. That's what you have to do. So you can start by finding whatever angle you want. It doesn't make any difference. Let's maybe find A. Okay, I mean, why not? So if I did that, right, what version of the law of cosines, involves capital A? Well, that would be this version, right? So you're going to use this version, right? So I'll plug everything into there. So I have, so 6 squared is equal to 9 squared plus 4 squared minus 2 times 9 times 4 times the cosine of A. Okay, and you just have to solve this equation for angle A, just like we did, right? Isolate this term, right? Subtract these two guys on both sides, get this term by itself, divide by this number here, get the cosine of A by itself, take the inverse cosine, that'll give you angle A. And then once you've got angle A, how do you find angle, say, B? Well, you just do exactly the same thing, right? You use the law of cosines again, right? Except you'd use the version that has angle B sitting inside of it. And then once you've got two angles, you subtract them from 180 to get to the third angle, and that's it. So in summary, there are really, I would argue, 4 kinds of triangle data that you could be given. One type is where you have 2 angles and a side. That's maybe the easiest case. You should use the law of sines for that. The next case is what we talked about yesterday, where you're given 2 sides and an angle, where the angle is not in between the 2 sides. You should use the law of sines on that one. Okay, that's the ass backwards case. It's the ambiguous case where there can be like 0, 1, or 2 solutions. For the remaining cases, that's side angle side. That's where you have 2 sides and an angle in between the 2 sides. And 3 sides, you should use the law of cosines. Okay, and don't mix and match these within the same triangle, right? Just use the law of cosines on these guys. Just use the law of just use the law of sines on these guys. Just use the law of cosines on these guys. Okay.